Let's just jump right into this explainer. We're tackling what is honestly the biggest problem in AI generation right now: the silence. I mean, think about it. For all the absolutely incredible strides we've made in creating photorealistic motion, the outputs, they're fundamentally incomplete. We are literally still living in the silent film era of generative AI.
So look at what we're usually dealing with here. On the left, standard text to video. It's visually stunning, sure, but without any environmental sounds, foley, or speech, it just totally lacks emotional resonance. And then on the right, you've got the current workaround, sequential pipelines. This is where you generate a video first and then rely on a completely separate model to try and guess the audio, or vice versa. It's like duct taping audio onto the video after the fact, and it always creates this mismatched content. You miss out on all those crucial bidirectional cues, like the realistic reverberation of a room, or, perfect lip sync, which is exactly why LTX-2's unified architecture is such a massive breakthrough. It generates both vision and sound at the exact same time. To see exactly how LTX-2 pulls off this magic trick, we're going to look under the hood at 5 key areas: compressing signals, thinking tokens, the dual-stream architecture, CFG alignment, and finally, hardware efficiency. Let's get into it.
Section 1. Compressing signals. Preparing the raw data.
Okay, so before the AI can jointly generate sight and sound, it actually has to know how to efficiently process them, right? A lot of previous models tried to force both video and audio into one shared space, which is honestly incredibly inefficient. It's like trying to fit a square peg in a round hole. Rather than doing that, LTX-2 uses decoupled modality-specific VAEs. You can basically think of them as specialized translators. One optimizes for the massive 3D space of video, while the other perfectly handles the 1D timeline of stereo audio.
Taking a 30,000-foot view here, you can trace that yellow audio pathway up at the top and the blue video pathway down at the bottom. Notice how they're being encoded into their own distinct, highly efficient latent tokens right from the very start. This decoupling is absolutely foundational. It's what allows LTX-2 to precisely control exactly how much computing power goes to vision versus sound later on in the process. Moving on to Section 2, Text Conditioning and Thinking Tokens, Grounding the AI. Now, imagine you want a character to speak with a very specific accent and have flawless lip sync. A simple text prompt just isn't going to cut it, is it? To handle this, the system uses a 3-step feature extraction process. It scales, flattens, and projects the data using a Gemma 3 multilingual encoder. To put it simply, it isn't just reading your prompt. It's fully digesting every little phonetic nuance and capturing incredibly complex semantics before it ever even starts drawing a single pixel.
And here's where it gets really fascinating. Notice the thinking tokens appended down at the bottom of the text embedding block. These act as global information carriers, and their job is to drastically improve phonetic and semantic accuracy. Instead of just lazily passing along empty, padded data like older systems might, LTX-2 swaps those padded positions out for these learnable thinking tokens. They actively aggregate missing details and context, making sure that the final generated speech doesn't just match the movement of the lips, but perfectly captures the exact natural cadence and tone you were asking for.
All right, Section 3, the dual-stream architecture, the magic of synchronization. So this is where the real magic happens. Think of this transformer backbone as 2 interconnected brains. You've got one for video, one for audio, and they are constantly, and I mean constantly, exchanging information via bidirectional cross-attention layers. Instead of running sequentially one after the other, these streams denoise the latent data in parallel. They are cross-referencing each other at literally every single step of the generation process.
You'll definitely want to notice the asymmetry here. LTX-2 dedicates a whopping 14 billion parameters to the complex spatiotemporal dynamics of the video stream, while keeping the audio stream highly efficient at just 5 billion parameters. It uses a 3D positional embedding for the video to actively track space and time, and a 1D embedding for the audio timeline. And this makes perfect sense, right? By doing this, LTX-2 avoids over-parameterizing the audio pathway. It perfectly balances the computational load, giving you high visual fidelity without wasting precious resources.
Let's look at how this plays out in practice. This cross-attention actually physically tracks a moving vehicle across the spatial grid to map visual cues directly to the resulting environmental Foley sound. Because those video and audio streams are continuously talking to each other, the sound of the engine passing by matches the physical location and the speed of the car on screen with subframe precision. It's just wild. And it gets even more granular when we're talking about human speech.
The cross-modal attention dynamically shifts its focus between two different speakers' lips to guarantee that sub-frame perfect lip sync. The AI knows exactly who is speaking, it knows where their mouth is, and it generates the audio waveform perfectly in sync with the visual generation.
Which brings us to Section 4, Modality-Aware CFG, fine-tuning the alignment.
During inference, LTX-2 uses what's called modality-aware classifier-free guidance. You can basically think of this as the steering wheel of the model. It independently modulates the influence of your text prompt and the intermodal alignment. You see, standard AI models use regular CFG just to make sure the output matches your text prompt. But in a joint audiovisual model like this one, you also have to make sure the audio and video actually match each other.
So here's a quick breakdown of how that works. You have SS, T for textual guidance, and then this powerful new term, SSM, for cross-modal guidance. The crucial takeaway here is that by tuning that cross-modal guidance term, we actively force the dynamic and contextual information between sight and sound to match up perfectly. If you dial up SSM, you get tighter temporal synchronization between the generated video and the audio track. As a creator, this gives you total, granular control over the final audiovisual alignment.
And finally, Section 5, Hardware Efficiency and Inference, running LTX-2.
Now, you might be wondering what kind of supercomputer you need to run an integrated 19 billion parameter model like this. Astonishingly, on a single NVIDIA H100 GPU, LTX-2 is 18 times faster than a video-only model like WAN 2.2. Just let that sink in for a second. It is generating highly complex video and perfectly synced stereo audio 18 times faster than leading video-only competitors, all on a standard high-end enterprise GPU. And thanks to that incredible efficiency, it's capable of generating up to 20 continuous seconds of synchronized stereo video. That absolutely shatters the temporal limits of both the proprietary and open-source models we have out there right now.
How on earth does it achieve that kind of efficiency? Well, it's all thanks to a multi-scale, multi-tile inference strategy. First up, it generates a base latent representation at a lower resolution, about 0.5 megapixels, just to establish the scene and sync up the audio. Then it scales that up. Finally, it renders those complex 1080p visuals in overlapping tiles, so it never blows out your GPU's memory. Those tiles are refined independently and then blended together seamlessly before the final VAE decoding. And that, my friends, is exactly how you get Hollywood-level audio-visual generation running perfectly on a single H100 chip.
Ultimately, LTX-2 proves beyond a shadow of a doubt that we don't have to choose between stunning visual fidelity and rich immersive soundscapes anymore. We have finally moved past the era of silent visual spectacles and stepped into the world of true, unified audiovisual generation. Which really leaves us with one massive, exciting creative question to end this explainer on. As AI learns to natively see and hear in perfect sync, what stories will you tell?